Hi, this is gonna be the last problem from chapter 6 that we're gonna cover. So a capacitor in an RC circuit is being charged by a battery of EMF. So we're supposed to find the total energy supplied by the battery, the total energy dissipated by the resistor, the total energy stored in the capacitor, and it's asking us to find the fraction of energy that's supplied by by the battery, and that's in comparison to the total energy stored in the capacitor. It's gonna be the easiest one actually for any of these. Okay, cool. So we're gonna go ahead and do A. So first, let's have a visual. Let's have a visual of what's actually happening in the circuits. And by doing that, we need to draw the circuits and what's actually happening in it. So we have an EMF source in series in an RC circuits. Cool. So we have our resistor and then our capacitor, and it's very simple. So it's just like this. And then since we're looking for the total energy, we're just going to be using P equals I, and then it's going to be delta V, which is going to be, so this is how we find the energy supplied by the battery. So delta V actually gives us very different value. So we have our delta V battery. It's going to be EMF minus IR. We have our delta on resistor, which is going to be IR. And then we have a delta for V cap is going to be um, Q is equal to CV. So V is equal to Q over C. Cool. So, so basically, one thing to notice is that our circuit is being charged. So since our circuit is being charged and we're trying to find the total energy for all of these, we're assuming that our time eventually goes to infinity. Because the time is equal to infinity, or a very long amount of time, eventually we're going to reach the total energy for all of those. Very, very, very simple if we know what we're doing, right? So find the total energy supplied by the battery. So by the battery, we're just looking at this. EMF minus IR. We don't have an internal resistance for the EMF. So we can just say that the internal resistance R, small r, is equal to 0. So we can actually just rewrite P over here. I think this, no, I don't want this more. I'm going to use red. We're going to go ahead and write power, but in terms of the V battery. So we can write P is equal to I multiplied by the EMF. That's what we're doing. But since since this is a function of time, we can just go ahead and just do P of t is equal to I of t multiplied by the EMF. Where I of t, when we are charging a capacitor, I of t is equals, I believe it would be EMF over R be the maximum charge on the capacitor would be the EMF over R, and then we have 1 minus, oh no we don't, that's the other one. So it's going to be 1 minus for the charge, but for the currents, it's just going to be E negative T over RC. Cool, very, very simple. Okay, great. So for this problem, it's asking us to find the total energy supplied by the battery. So we're supposed to find the energy accumulated over time. So to find that, we need to integrate. So we're going to have to integrate P of t with respect to t from 0 to infinity. This is what we need to do. So we can just write the integral from 0 to infinity And then we have our EMF times R here. It's going to be your I of t first, times E negative t over RC, times EMF dt. The EMF and the R are constant, so we can go ahead and just pull those out. So we have EMF times an EMF. We have an EMF squared times R. Then we have the integral from infinity to 0, or from 0 to infinity of e to the negative t over RC dt. And the integration of e to the t is just e to the t, or I should say e to the x is just e to the x. But if it's e to the negative t over RC would be in the numerator, so we can go ahead and just rewrite this. We can go ahead and just rewrite e squared over r. And then we can go ahead and just do an RC over 1. And then we have e to the negative t over RC from infinity to 0. Very bad. R's cancel. So then this would just give us e squared c. Or I should carry the negative over here. So negative e squared c. And then e to the infinity. Sorry, e to the infinity is 0. Minus e to the 0 is 1. So our negatives actually cancel, and we're just gonna be left with e squared over c. I mean, not over c, but e squared c is gonna be the total energy supplied by the battery onto the capacitor. Cool. Okay, cool. So we can go ahead and just erase all of this. So we have our answer for A, which is e squared c. And let's move on to the second one. The power dissipated by the resistor. So we're actually just doing the same thing here. We're going to find the P of t dt from 0 to infinity, but this time P of t is different, because now we're looking at the voltage across the resistor, which is going to be IR. So we have Pt equals I of t squared times R, basically, right? So we can recall that I of t is just EMF over C it's EMF over R times e to the negative t over RC times R from this, right? And we're actually squaring this. We're getting rid of this, and we're getting rid of one of the R's here. And since these are constants, we can just pull the constants out. We have infinity 0. Same thing as earlier. And from 0 to infinity. And then we have e to the negative 2t, since we're squaring this, RC dt. Cool. So again, a very simple integration. We're going to be left with e squared over r, and then our constants RC goes on top, and then we have a negative 2 at the bottom. So the r's are going to cancel, but it's going to leave us with a negative 2 on the bottom here. And then it's going to be e negative 2t over RC from infinity to 0, which is the same thing. So this is going to equal, so this is just negative 1. So negative times a negative, that would actually just cancel. So it's going to be e squared c over 2. This is our power dissipated by the resistor. Cool. That's good so far? Cool. So now for C, we're actually finding the total energy supplied in the capacitor. So far what we've done is the total energy supplied by the battery on the capacitor, by the resistor on the capacitor. So now we're going to find the total energy stored in the capacitor itself. So we do have an equation for energy. I believe it would be Q squared over 2C, where Q is the charge, and 2cc, it would be just the capacitor. Just the capacitor. So we can recall that our Q is equal to just CV. So we can say that U is equal to C squared V squared over 2C. Cancel the 2's actually, so U is equal to CV squared over 2. Where V is actually just the EMF. So final answer, U is equal to C EMF squared over 2. So actually, we can just see that the total energy supplied by the resistor, or sorry, the total energy dissipated by the resistor is the same as the total energy stored in the capacitor. It's pretty interesting because that's really what we're after at the end. So since we have these values, so what fraction of energy is supplied by the battery is actually stored in the capacitor? So the fraction of energy supplied, so fraction, automatically we're thinking of a fraction, cool. So we're gonna go C. So this is the energy supplied by the actual capacitor, stored in the capacitor. This is stored in the capacitor, all divided by E squared over C, which is going to be the total energy supplied by the battery. And from here, we can just say that this cancels, C's cancel, and then we could just be left with 1/2. So in the end, we can say that 1/2 of 1/2 of 1/2 of the energy supplied by the battery is stored in the capacitor. Or we can just take a look at it. I mean, this multiplied by 1/2 is just equals to this. So it's the same thing. But yeah, that's it for this one. Thank you.